In this video, we're going to work example problems related to solids of revolution. So we're going to find volumes of solids that where these solids are obtained by rotating an area about an axis. And so solids of revolution were brought up in the opening section on volume. And in this section, we developed the integration method for finding volume given by this formula. So you integrate from a to b, a of x dx. And what this means is that, so the independent variable doesn't have to be x, but you're let's say it is, and you're integrating from x is equal to a to x is equal to b. The solid a and b are like the front and back end of the solid, and each point x, if you evaluate this formula at each point x between a and b, then this function here represents if at that point x you had a plane that was perpendicular to the x-axis and it cut through the solid, there would be a cross-sectional area. This is the area of that cross-section. And so you can imagine you would have a unique cross-sectional area for each x point between a and b. And so when you multiply that cross-sectional area by delta x, you can see that each element that you're breaking up the solid into is a right cylinder. A right cylinder is just, you've got two planes that are separated. They're parallel and they're separated. The planes can be any shape, not just circular, any shape. And then the solid is made by these perpendicular lines that connect the two planes. Not just on the edges, like throughout the entire plane, so you have this non-hollow solid. That's a right cylinder. And so with this method, that's how we're getting the volume. We're breaking up the volume into right cylinders, into a large number of right cylinders. And that's what solids of revolution is based on. It's based on this integration technique. We're going to be breaking up the solid of revolution into pieces of right cylinders. Now, solids of revolution aren't the only application of this formula. This is a general formula that you can use for any shape to calculate volume, assuming you can get this cross-sectional area formula. But it's still important to know what integration formula we're using, because we're going to see in the next section that, so this integral for finding volume is a good integral, but for certain circumstances, this doesn't work so well. So in the next section, we're going to develop another integral. We're going to be breaking up volumes into other kinds of differential elements and creating another integral. So just note that this is the volume integration technique that we're using. This is the first volume integral that the calculus book developed. Okay, but in this video, we're focusing on solids of revolution. And what we want to do is, for each problem, we're given a set of curves, a set of equations, and there's going to be an area bound by these curves, and we want to revolve that area about the axis that's given. And the goal is we want to calculate the volume that's generated by revolving the area contained within the given curves about the given axis. And again, to do this, for solids of revolution, you use this formula here for volume. At least that's what's recommended. I mean, technically you could do whatever you want as long as the integration works, but that's what the textbook recommends. All right, so okay, here's y is equal to x plus 1. Here's x is equal to 0. Here's y is equal to 0. Or no, here's x is equal to 2, and here's y is equal to 0. So we're revolving this area about the x-axis. And so we want to think about the solid that's created by doing this revolving process and calculate the volume of that solid. And so we want to think about the solid that's generated by this revolving process and calculate the volume of that solid. Okay, so again, we're going to use this formula, and what are we going to have as the independent variable? We're trying to generate these right cylinder pieces. What's going to be the independent variable? Well, it doesn't have to be x, it could be anything, but here we can choose x, because then we'll have, for each x, we could just use this line here for the function to get the cross-sectional area formula. So the cross-sectional area formula, if we imagine this is a piece here, okay, the cross-sectional area formula is going to be, so if we write out the Riemann sum, so we're going from I is equal to 1 to n, the cross-sectional area formula So if we imagine this solid is already created, and we're at this position here, and we can pick any point within the interval with any x, the midpoint, left or right endpoint, whatever. What's the cross? If a plane that's perpendicular to the x-axis, and and it's crossing somewhere through here, and so it cuts through the solid, what's the cross-sectional area that it creates? Well, it's going to be a circle with radius equal to this, right? So what is this length? This is x plus 1, whatever this x is. And so the area of that circle is pi r squared. And this is the radius, so it's pi times x plus 1 squared. That's a of x. That's this. Well, we want to put the xi star. Meaning xi star, let me rewrite that. Xi star means you can choose any point, any x you want within this interval. So that's the a of xi star, okay? And then times delta x. It's always delta x. It's just delta the independent variable, these equal width intervals. And when you do that, when you multiply by the delta x, what happens? You get that right cylinder. I mean, that's the idea. When we talked about this, when you're doing integration, you have the quantity you're looking to solve for, and you're going to break up that quantity. And so in that case, the individual pieces are going to be the same thing as the main quantity. So in other words, we're trying to solve for a volume, and therefore the pieces we break it up into are going to be little volumes. And then we're going to add up all the little volumes. And so there you go. That's the Riemann sum. If we chose n is equal to 10, we would have an approximation. But what we're doing is we're going to take the limit as n goes to infinity. And so with that, we can convert this into an integral. So this infinite sum here turns into this elongated s. We put the limits of integration. We're going from 0 to 2. Now, since we took the limit as n goes to infinity, there's no more xi star. The point you choose doesn't matter, so we just put the function. So pi x plus 1 squared. And then delta x is b minus a, so 2 over n. As n goes to infinity, delta x becomes infinitesimally small, dx. That's the volume. Okay, so we've got from 0 to 2, we can bring the pi out front, x squared plus 2x plus 1 dx. Okay, so integrating, we've got 1/3 x cubed plus x squared plus x. Okay, we're going from 0 to 2. Okay, so 2 cubed is 8, so 8/3 plus 4 plus 2. And then that would be minus 0. So we've got pi 8/3 plus 6. This is pi 8/3 plus 3 over 3 times 6 is 18 over 3. So this is 26 over 3 pi. And there you go. That's the volume. Okay, so the area contained within the curves x is equal to 2 squared of y, which is this. X is equal to 0, which is this. And y is equal to 9. So this area rotated about the y-axis. All right? So as a solid of revolution, we're going to use that, this formula. Okay? But what do we want? Actually, okay, do we want x to be the independent variable? Well, in that case, we would be breaking this up from 0 to 6. Okay, if we were rotating about the x-axis, then maybe so. but we're rotating about the y-axis, and it's not like we couldn't use x as the independent variable. And I think this would be a good topic to have another video about, to see, could we do this, find this volume, rotating this area about the y-axis with the independent variable as the x-axis. We might be able to do that, but what would probably happen is when we set it up, we'd realize, okay, we're deviating from this developed formula. And so it doesn't mean that we can't do it, but we would kind of be making up our own integration. We'd have to, we don't need to, whenever we calculate these volumes, once we get the cross-sectional area formula and it's set up like this, we don't need to check if it converges or anything. It's already been proven that it's going to converge. We've already proven this method. So if we did this, it would be like, we might have to make, the cylinder would be, I'm not sure if this would work, how you would do it. So like this would be the cross-sectional area for each x. That's like the cross-sectional area. And then this would be the d. I don't know. I mean, maybe you can't do that. I'm just saying that. I'm just trying to point out. I'm trying to generalize this as much as possible for you. But okay, here we're going to need to have y be the independent variable. Okay, because we're rotating it about the y-axis. That's the main reason. And what we'll do is it will, so this would be like a dy, and you have the function evaluated at some y value. And it's x as a function of y. You input a y, and it gives you, this is x. And so this is the radius. It's going to be pi, each a of y is going to be pi times whatever this value is squared. This is, for any x value, this is 2 root y. So a of y is pi times this squared, right? A of y is pi times 2 root y squared. So 4 pi y. That's a of y. But when you do delta y, that's when you get the right cylinder, right? It's the exact same method. It's this volume, right cylinder volume formula, just with y as the independent variable. Okay, so we're going from a is equal to 0 to b is equal to 9. And I mean, that's it. So the volume is 4 pi y dy. There you go. So now we just need to do this integration. So this is 2 pi y squared, evaluated from 0 to 9. Right, this derivative gives 4 pi y. So we've got 2 pi times 81, and that's it. 162 pi. Okay, we want to rotate this area, the area contained between y squared is equal to x and x is equal to 2y. Rotate that about the y-axis. So, we're rotating about the y-axis, so we want to use, it most likely is going to be, we want to have y be the independent variable. Okay. And so what's the area formula going to be? Well, in this case, so if this, we're integrating from a is equal to 0, so a is equal to 0 to b is equal to 2. So in this case, a delta y. Here's a delta y. What's the area of the cross-section going to be? Well, we're going to get a right cylinder with a hole in it, like kind of like a washer. It'll be, It'd be like that, like a washer. And why is that? Because if you're rotating this area about the y-axis, then what you're doing is you're not including this. Okay, so what's the cross-sectional area of this washer here? It's pi RO squared minus RI squared. So with this being RI and this, right, that's RI and that's RO. So the A of X is equal to pi, or no, it's going to be A of Y. The A of Y is equal to, so pi, and then, so we've got, so if we solve for Y here, this is plus or minus root X, but I guess we can ignore the minus, I'm assuming. Yeah, because minus root X would be over here, right? The idea is what they're saying with that, with y squared is equal to X, if you came to y is equal to 1. Like this equation, y squared is equal to X. When y is equal to 1, or no, okay, no, actually we don't, no, this is, no, we leave it like this. This is just X is equal to y squared. So yeah, it's y, just y squared. That's, okay, wait, no. The outer radius is, for any given y, the x, that we're looking for the x value. What is this x value equal to? That x value is equal to 2y, so we do 2y squared. Okay, minus, and the RI, which is y squared. You see, this is this for the given y value, for any y value, the function of y, if you do y squared, that's this x value. If you do 2y, then that's this x value. So we do pi RO squared minus RI squared. So we've got 4y squared minus y to the 4th. There's A of y, so there we go. So now we're going to go from 0 to 2. The volume is equal to dy. So this is pi okay. So now just evaluate the integral. So this is 4/3 y cubed minus 1/5 y to the 5th. Okay, evaluate this from 0 to 2. Okay, so this is 2 cubed is 8. 8 times 4 is 32. So 32 over 3. 2 to the 5th is 32 over 5. And then that's going to be it. So 32 over 3 minus 32 over 5 is 64 over 15. So 64 pi over 15. Okay. The curve contained between 1 plus secant x and y is equal to 1 plus secant x, that's this, and y is equal to 3, which is this, rotating it about y is equal to 1. So this is a little different. We're rotating it about this axis here. But this is still simple. This is just this is where the center of the radius is going to be, the center of the circle of each cross section. So we're going to take, we're going from here to here, which is, what is that? We need to solve for when 1 plus secant of x is equal to 3. So when does 1 plus secant x equal 3? Solve that for x. Okay, when n is equal to 0, you got minus pi over 3 to pi over 3. And that should be, so pi over 3. Yeah. So we're going from, this is minus pi over 3 to pi over 3. Okay. So the cross-sectional area, like if this is a dx, then it's just going to be, this is the inner radius, this is the outer radius. No. This is the inner radius right here, and then the outer radius, so there's the inner radius, there's the outer radius. That's it. And it's just going to be based on, you know, this is 1 plus secant x, this is 3. It's going to be based on those formulas. So a of x is equal to pi times 1 plus secant x squared. No. 3 squared 9 minus 1 plus secant x squared. That's it. So let's simplify this. We've got pi times 9 minus 1 plus secant x plus secant x plus secant squared of x. Nine minus 1 minus 2 secant x minus secant squared x. 8 minus 2 secant x minus secant squared x. Okay, so there's a of x. So now we do minus pi over 3 to pi over 3. And we can bring out the pi. And we've got 8 minus 2 secant x minus secant squared x dx. And so let's see if this has any symmetry, because we're going from like minus a to a. So let's see, 8 minus 2, this should be an even function, secant x minus secant x squared. Okay, so now if we put a minus here, we should get the same formula, and we do. So we can write this as, bring out a 2, so 2 pi, and then do 0 to pi over 3. Okay, so 2 pi, and we've got 8x minus, what is the integral of secant x? Well, you know what? This isn't a lesson on evaluating definite integrals, so I don't want to waste too much time going through this integral. So let's just plug this, 8 minus 2 secant x minus secant squared x. Let's just let the calculator do this. So there's the function. Now we want to do the definite integral from, we're going from 0 to pi over 3 okay, times 2 times pi. Okay, something is messed up, and what I messed up is that this R outer, okay, so we got pi, and then what is the R outer? Okay, so we want to do R outer squared. What is this RO? We got to be careful here because we're rotating about y is equal to 1. The function is relative to, you know, to the actual x-axis. So the function is, we're actually, you know, I probably didn't draw this the best, but we're breaking this up. This is the independent variable axis. So we need to calculate RO and RI relative to the function evaluated from here. And so what we're doing is we need to take, it's 3 minus 1. For, okay, yeah, so we get 2. This is 3 minus 1. I'll write this out. So obviously it's going to be this line here, or this RO for every single delta x is going to be 3. It's going to be 2. 3 minus 1, this distance is 2. Okay, but what about the RI? The RI is going to be, so this is squared. The RI is going to be 1 plus secant x minus 1 squared. Right? You take, for any x value, you take, this is 1 plus secant x, this length. That's 1 plus secant x. You subtract from 1 plus secant x 1 to get this length. And then we want to square that. R outer squared minus R inner squared. Okay, so we've got 2 squared is 4. Then here it's just 1 plus secant x minus 1. That's secant x, so just 4 minus secant squared x. Okay, there we go. So there's the a of x. So we're going from minus pi over 3 to pi over 3. We can bring the pi out front. 4 minus secant squared x dx. Okay, now since we're going from like minus a to a, this looks like it could be an even function, so let's check that. 4 minus secant x. Okay, so f of minus x is equal to f of x here. So we can, this is an even function. 4 minus secant squared x is an even function. So we can take out a 2 and rewrite it this way. Okay, so now evaluating this. So we've got 4/3 pi minus tangent of pi over 3. And that's the volume. Okay, last problem. We want to rotate this area contained within these two curves about x is equal to 3. Okay, so we're going to treat y as the independent variable, and we'll integrate from 0 to this value where they meet here. And so what value is that? So we need to set these two equations equal to each other. Okay, so plus or minus 1 over root 2, but here we just need the positive. So b is equal to 1 over root 2, a is equal to 0. Okay, so here's a delta y, and so what's the a of y going to be? Well, this is our outer, and this is our inner. So we just need to represent these. It's pi r outer squared minus r inner squared. So what is r outer? So this is x is equal to y squared. This is x is equal to 1 minus y squared. So what is this RO? If as a function of y, what's RO? Okay, well, it's going to be 3 minus, it's 3 minus this value here. So 3 minus y squared squared. Okay, what's R inner? It's 3 minus this value. So 3 minus 1 minus y squared squared. So now let's just simplify this. 9 minus 6y squared plus y to the fourth minus, then we've got 3 minus 1, so then 2, it's plus y squared squared. Okay, so we got 9 minus 6y squared plus y to the fourth minus 4 plus 4y squared plus y to the fourth. So we've got 9 minus 6y squared plus y to the fourth minus 4 minus 4y squared minus y to the fourth. Okay, so we've got plus y to the fourth minus y to the fourth. Then we've got 5 minus 10y squared. Okay, so now we can use our calculator here. So we've got pi times 5 minus 10 times y squared. Okay, so let's store this. This e, now we want to integrate from 0 to 1 over root 2 with respect to y, that equation. So, okay, and I just noticed, so we're going from minus 1 over root 2 to 1 over root 2. So let's do this again here. Ten pi root 2 over 3. So this volume is 10 pi root 2 over 3.